Okay, so Fitch algorithm. So it's going to be yet another algorithm in this session. I hope you are not too afraid or you even enjoy it. These are simple algorithms, but it's important for you to understand that the evolution of the ideas and of the techniques and of the methods in phylogenetics during the 20th century has as at its core these kind of algorithms, and that's what makes it possible nowadays to just click on a button and have a very good phylogeny with bootstrap support, etc., etc. That software is busy calculating for us. So these very simple algorithms, UPGMA, and here we're going to see Fitch algorithm for minimum evolution, are the building blocks on which researchers have later built more elaborate algorithms for tree inference. So let's go with our Conrad Fitch. Very simple. So at the beginning you have a score counter. Okay, you start your score counter at 0. In any node, you're going to go bottom to top, again like UPGMA, but here the tree is already built, right? We're not trying to find a tree, we have a tree and we are going to try and calculate this parsimony score on it. So on every node K, you have a set of acceptable, so-called acceptable characters C subscript K. We're going to define how it's made. For the leaves, the acceptable characters are just what you see in the leaves. Okay, so CK is the singleton, the set composed of one element that is the character seen in the alignment on that leaf. Okay. We are busy here calculating the parsimony score for one column, right? And the total parsimony score will be the sum over all the columns in our alignment. Here, Fitch algorithm talks about the parsimony score for one column or one side of your alignment. So we have one character per leaf. Moving up from leaves to root, this is called also post-order traversal, and you'll see this maybe in maximum likelihood methods. In any case, when somebody talks to you about a post-order traversal of a tree, you must understand it's from the leaves to the top, to the root. When K is a node with sons I and J, you will define that your set of acceptable characters for the node K is the intersection of the sets of acceptable characters for its two sons, in case that intersection is not empty. If the intersection is empty, then the set of acceptable characters for the father is the union of the acceptable characters for the two sons. Okay, so it's not very complex. It just asks you to remember what is the intersection of two sets and what is the union of two sets. Okay, and then in case the intersection is empty, then you have this operation you perform on S. Very important. S is equal to S plus 1. Okay, you update your variable S, adding 1 to it. You increment your variable S whenever you witnessed that an intersection of the two sets of acceptable characters for the two sons was empty. When you move up to the father, you add 1 to your counter for your parsimony score. Once the root is reached, S is the total parsimony score for that, or the parsimony score for that site, and the acceptable sets on the nodes define most parsimonious histories. And we'll see how to build these most parsimonious histories from the sets. Okay, so let's go on an example. I take this site or this alignment, and what I'm given is this tree. Okay, it's not very beautiful. It's It's probably, yeah, quickly drawn by hand using one tool or another by me. Maybe we can say it's a tribute to Paint, the software by Microsoft that is soon going to disappear. It's in the news lately. So yeah, it's good to build old school phylogenies just with an electronic pencil. Okay, so you have a set phylogeny and you have a set of characters on the leaves. The score is initialized at 0 and you will move from bottom to top. Okay, so you'll have to decide. You can start with these two or you can start with these two, moving from bottom to top. So let's go. First step. So we're not going to decide, we're going to perform them both almost simultaneously. Here the set of acceptable characters on this leaf is the singleton A. The set of acceptable characters on this leaf is the singleton C. Okay, so I move to the father. Is the intersection of the two sets empty or not? Yes, it is empty, because here I have singleton A, here I have singleton C. The intersection is empty. So I decide that the set of acceptable characters for this father is the union. But whenever I use the union instead of the intersection, simultaneously I modify my score. I increment my score. Okay? So here I label this node, this father node, with the union AC. The story is different here for these two sons. It's labeled T here, so set of acceptable characters singleton T, set of acceptable characters singleton T. What is the intersection of singleton T with singleton T is singleton T, right? So the intersection is not empty. So I'm happy, and I use the green color to say I'm happy. I label this node with the singleton T, and I do not modify my score. My score is 1, okay? So I've gone up this way and up this way. I will still have to go through this node, up, 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 and then finally here. So next step, here on this side, what's happening? I have here one son. Okay, this node has two sons. One is here and the other one is here. The first son has set of acceptable characters, AC, as a set of two elements. Here I have a set of one element, A. What is the intersection between these two sets? The father sees that the intersection is singleton A. AC intersection with singleton A is singleton A. This intersection is not empty. So I'm happy. Green color, I do not modify my score here. So the score was still 1. Now here what's happening? I have T here, that's one of the two sons of this node. The other son is here, and the other son has a set of acceptable characters, singleton A. So the intersection of singleton A with singleton T is the empty set. Since I have the empty set, I cannot use it. So I label with not the intersection, but the union. The union is A and T, the set of two elements A and T. And so I update my score. Remember from the previous slide it was 1, now it's 2. Right. Then next step, you know the drill. Here I have A, here I have singleton T, so the intersection is empty between singleton A and singleton T, so I use the union, I update my score to 3. And I label this with the union, right? I have AT union here, here I have also AT, right? So the intersection of these two sets is the set AT itself. So I label my root here with AT. It's a rooted tree here. So my final score for this, my final most parsimonious score for this tree is equal to 3. Okay? And the Fitch algorithm leaves me also with labelings for all the nodes. And we're going to see now in the next slides how do I build a possible evolutionary history using these labelings. and ensuring that ultimately the number of blue bars I will have on this tree, meaning the number of inferred evolutionary events, will be equal to 3. So what you do is just you go now from top to bottom, and you'll see that if you have the choice, take one at random. Okay, at the root you have the choice, so take one at random, A or T. Right, but then when you go down, if you can preserve the character that you had, then preserve it. Otherwise, you will be forced to change. So here, I chose to, whenever I have the choice between A and T, I just randomly choose A. But you would see that if you decide to start with T, it would work also the same. You will get a history with minimal score of 3. Okay. So here, if I choose A, now when I go down, I will decide to choose also A. As I said, when you have something, you have a node that is lower than you go from top to bottom, right? In a pre-order traversal this time. And if you can, you first decide on something, and if you can, you conserve it when you go down, right? So here, if I decide A, I will conserve it. I will have A here. Here I will label with A, it's fine, it's possible. And here I can also conserve A, so I keep it A, right? Okay, so here I have labeled with A, and A. Going down here, I label with A here, I label with A here, because I had the choice between A and T, but since the father has A, I choose to preserve A, okay? So I have A here. And finally, to come here, I don't have the choice. I cannot keep A, so this is labeled T, right? So this is the history we have, A, and here A and T. Now let's put our blue bars transformed into red bars, sneaky color changing bars. Now it's red, okay. And here you have A, here you have T. Basically you put a bar whenever you are on a branch whose vertices connected by this branch do not bear the same label. Okay, so it means there is a substitution. So here there is one inferred substitution from A to T. Here there is one inferred substitution from A to T. And here one inferred substitution from A to C. All other branches who do not have a red bar have the same character on their two nodes, the two nodes that are connected by this branch. Okay, so here A, here A, etc. And that's a miracle of Fitch's algorithm. How many red bars do we have? We have indeed 3, while our algorithm had predicted that the most parsimonious history is a history with score 3. Okay, so remember, Fitch's algorithm enables you to calculate automatically without hesitating, without calculating so many different possibilities, just automatically going in one post-order traversal from bottom to top, calculating in just one traversal the parsimony score, and then one other traversal from top to bottom to decide on a possible history or a possible labeling of the internal nodes. Right. Okay, program for the next session. We'll see heuristics for an efficient travel in the space of trees, looking for the best tree. So how do we explore this set of so many possible tree topologies without obviously going through each and every of them? We're going to finally define what is the likelihood of a tree. I already talked about it a little bit in the question and answer session of session 2. We'll see what's the maximum likelihood framework and how does it work to build the maximum likelihood phylogenies. We'll see Bayesian methods, and we'll see how to assess the quality of a tree, so the bootstrap method and local confidence statistics to assess confidence values to the branches in our in an inferred phylogeny. So it will be exciting and also full of different stuff. So yeah, stay tuned, enjoy your practical, and see you soon.